So now the next session will be Dr. Ajith Rajiva. He'll talk to us on the remote sensing. So how the whole concept of the GIS, which offhand many of us use. So how do we use this remote sensing, and all these morning classes are absolute theoretical. So afternoon we will actually put all those variables to use with R and other stats models. So over to Ajith for.
Good morning, everyone. I'll try not to take up too much time. I know these things are getting quite difficult to comprehend as we get towards lunch. But I just wanted to say, have everyone got this link in the WhatsApp? Why is MSN opening? Okay.
I think all of you in the WhatsApp group, you would have got a Google Drive link. Kindly, did anybody not get it?
Okay, so that's mostly for the afternoon workshop we're going to do. I think if you can just download the materials now itself, keep it with you, and then do it. Okay, so morning everyone. We'll start with GIS methods before we get into remote sensing. So we'll try and cover some of the basics for those people who may not know what these things are. How many of you know what GIS is in general? Hands up. 3, 4, 5, 6 people out of total. Okay, so this course is recommended for the rest of you. So GIS is basically Geographical Information Systems, which is how we model and sort of represent space in a two-dimensional place, and we live in a three-dimensional world. Yeah, so it's this. It collects, manages and analyzes data related to locations on Earth. We create maps, 3D scenes to visualize data to spatial locations and what's around it. We organize the information, and then we can collect that information, put it together into a database with other outcomes of interest that we're trying to study, and then we can make associations and we can draw conclusions from that. So the applications of GIS broadly are in disease surveillance, outbreak detection, health risk management, healthcare accessibility. We also create applications which are on the web, which will show maps of the whole country or particular regions to show how various parameters change over space and time. And then if there is space involved in your study, usually there is a GIS component also involved. So I think most of you know what this map is. Anyone here who does not know what this map is? So this is the John Snow cholera map, where he plotted all of the cases that were of cholera that were happening in this one particular neighborhood, and he then overlaid that with the blue information, which is the pipes, the water pumps that were there in that particular region. So he could find out that all the cases were related to this one particular pump. So he was using the maps back in 1854 to ascertain how the outbreak of cholera was happening in London. So basically, from the inception of epidemiology, we've been using GIS in some capacity to try and figure out like what the associations are between various exposures, which is in this case exposure to contaminated water, and outcomes, which is cholera. So I'll just go over what we will do quickly for this. We'll just go over the various different types of information, what kind of formats they will be available in, and coordinate reference systems. So this is just the basic terminology for GIS. If there's any doubts, just please stop me at any time. I'll try and explain things as best as I can. How many of you use Photoshop? Do you know what a raster is? Okay. So anyone have the mic? Just you can speak up. Data related to Image files, yes. So, but what is, yeah, do you know what a vector data and raster data is? Is there anyone who has known this beforehand? Or at least like colloquially, if you know what vector and rasters are. Okay. So rasters are just images, pixels, JPEGs, things that you will see like on a website. If you see an image there, you'll see this thing. Vectors, on the other hand, are also images, but they don't have pixels. They have instead point locations and directions. So when you store vector data somewhere, it is represented by location and the instruction of how to get there. So it's like coordinate plus path, and then it will keep doing that. So you can, what is the benefit of doing this is, if I were to zoom in onto that vector data, right, it's a line. A line has only one dimension. So if I zoom in infinitely, that line is still there. There is a very clear demarcation between the whole thing. What happens when you zoom into a JPEG? It starts breaking up, right? It becomes big squares. So we call that scale independence. So if you want something like a boundary, or if you want, you have some very clear demarcation about like catchment areas, for example, we will only consider people within this boundary and that boundary. You don't want to use raster data to try and define that boundary. You want to use vector data because that will give you a very clean yes or no, whether it falls within those areas. Raster, the thing is, if the boundary is raster, and say your pixel length is 30 kilometers or something like that, everyone who lives within that will also be included. So you have like a buffer area as a result of that. But yeah, so also vector data is just a regular table. So in R, when we come to that in the afternoon, we use this package called SF, and everything there is called ST underscore or something like that. ST here means spatial table. That will give you some idea of what kind of data it's dealing with. So anything that is called a spatial table is basically just a table, and it will have one column specifically geometry, which is points and coordinates. So you know that is vector data. So you can store multiple things in that table plus your vector data, and that stores all of that information. But raster data, you can only store it as a single layer. So it is X, Y, and the color. So far clear? So this is just to illustrate that fact. This is a vector image on the side. You can see very clear demarcations even if you zoom in. But if you zoom in on the raster one, you start seeing pixels. So raster, the analogy to think of is Lego blocks. They are built up of small tiny Lego blocks across a whole thing, and they will show you the image like that. Okay, so these are the different format types. They will depend on what usage use case there is. Certain formats are very good in compression, so you can store a lot of information in a small amount of data. So if you need to transmit that between people, that is more important. But if detail is very important, then you want something that can hold a lot of information and transmit a lot of information without having any loss. So we'll use several different types. So this is vector data formats. I think most people would have heard shapefiles. They used to be the industry standard for a long time. Shapefiles generally are 4 files together. Most people just think shapefiles are a .shp file. Please don't do that. It's all 4. It's .shp, .shx, .dbf, and .project. So all 4 of them comprise one shapefile. Then Google has its own proprietary vector this thing. So if you're using Google Earth or Google Maps, you'll see KML or KMZ, which is keyhole markup language. And you can see there, that's how it will be stored at. Generally speaking, they're mostly the same. They are storing point information or line information. And then currently what is now fast becoming the standard is GeoJSON. So GeoJSON, the thing that is great about it is highly compatible with other programming languages. Python uses it, R uses it, a lot of websites also use it. If you go on the government websites, all of the maps that they have got for point locations, you will actually find them as GeoJSON files. So they're usually ending up becoming the the next standard, I think. Shapefile will slowly get phased out after a while. But the other formats, CSV, Excel, how do we justify that? Can a CSV file be a vector? Speak up. If anyone needs to speak, just please give them a mic. Nobody wants to say anything.
If you want to add layer into it, like the number of cases, and we'll have the coordinates in the shapefile. So if you want to add layer into it, like number of cases in each and every places, so Excel or CSV will be helpful.
Correct. He's good. That's basically what will happen. So Excel and CSV itself, all of the tables there, all you have to do is then just provide a geometry for each of them, and then they will immediately become a vector. So even in the CSV format, you can save the geometry as a column within the data, much like JSON. JSON also basically is a column, is like a table format only, if you see the way it is stored. The only difference is it contains spatial information as well. So these are raster data formats. While technically speaking, JPEG, PNGs all are valid raster data formats, we don't typically use them for spatial analysis. And that's mostly because they don't contain spatial information in a traditional sense. So they have X and Y. But what does X and Y mean? Is X latitude, is longitude, is Y latitude? Is that, if you just get a JPEG and you put it on a map, it doesn't really know where it is, right? It depends on where you put it. That doesn't give you the spatial information. So we'll come to that, which is called coordinate reference systems. But typically speaking, we use the baseline sort of raster information that you will find online or in most databases is TIFF. TIFF contains all of that information in like a JPEG or a raster, plus the coordinate reference system to match. So basically then when you put that on top of your map, it will automatically align with where the X and Y values are supposed to be. So without that information, you have to provide it. So the other ones that you get are PNGs. PNGs in general do not come with any spatial information, but if you can provide the spatial information, or you know that 0x and 0y is exactly 0, 0 on the equator, then you can, all you have to do is tell the image to align with that and it will display on your map correctly. Then there is NetCDF, which is generally all earth science data, USGS data, which you download from websites, will be in NetCDF format. They are raster stacks. We'll talk about what they are later. Then there's digital elevation models, which is basically elevation as a single raster that come, but they have their own particular format called a DEM. Then currently HDF is also quite popular with a lot of earth data. And there are other images like bitmap and ECW. So these are, now come to raster stacks. So we said that in vector data, if you had multiple columns, you can store multiple sets of information about vector data. And in raster, we can only store one. To combat this, what you would do is have multiple rasters on top of each other, each representing one layer of information for the place that you are looking for. So for example, in this image, that's the real world, which you want to map and get information from. One layer of information is, say, land usage. This much is water, this much is land. But then you're not getting very much information about elevation on that. So what do you do to add that information? You add another layer, which has the elevation information. Parcels in this case is buildings. Where are the buildings? On top of that, you can draw lines on your raster and keep. Where are the roads? And then where are the people? So like that you can come, if you keep adding layers of information, you get more and more information about that one particular pixel that you're interested in. What is the downside of this? Yeah, so basically as you keep adding layers, you add more and more things for you to keep in mind for when you have to put the thing. and the size of your data starts increasing quite exponentially. Also, the other thing is, if you notice, the real world doesn't have pixels. So each one of those is going to be a generalization about one particular point. Say, for example, if you're saying 30 meters by 30 meters, a very good resolution, but a lot can change within 30 meters. So if you want to get the most perfect information, you won't get it like this. Anyway, so here's one thing that you can do. You can create these stacks, as I have shown here, by thematic groups with thematic content, which is basically what like information is breaking up. You can also do it by time. So So now forget that we have thematic content here. Just imagine this is all one variable. Just say it's temperature. Temperature at day 1, temperature at day 2, temperature at day 3, and so on and so forth. So if I were to put a map, put a point down here and say I want to collect the spatial information for that one person, you would get all of this information at once for that thing. So what have you built for that one person? You've built a time series, because that one person, and when you do the extraction of the raster information from that, you're getting every single point of exposure for every day that you have collected that information, and it is now attached to that one person. So if you have raster information arranged as a time stack, and you have point information like a vector of like a person or a patient or something, and you can combine those two on top of each other, you can then get a spatial time series like that. So that's one of the things that we will be doing as part of this project. Yeah, so one question. What's the most common raster stack in the world? If anyone can answer. If your notebooks are open, you're looking at a raster stack as well. What is that stack? TVs, projectors, they're all doing one thing. What are they doing? Is the information that is being provided to your screen one set of information? What is it? It's 3. You have red cones, you have blue cones, you have green cones. All of that are picking up only one thing at a time. So in order to, and the brain processes that information into a color image in your own head. In order for you to see those things, a computer also has to process a red image, a green image, and a blue image, RGB. RGB is a raster stack. It's actually black and white images of red, then blue, then green, and then they will tint it to particular colors and then combine. And that during that combination process, you get a color image. So that is a raster stack. People were doing that with film for a long time. Before they had access to like color images or specifically color film, they would just do that, superimpose that, tint the color, and you would get a color film. Pixels on your laptop screens do much the same thing. If you actually zoom into them with a magnifying glass, you'll see each of the small tiny pixels that are producing red, green, and blue. Okay, so just to summarize, most vectors will be comprised of 2 basic parts, a geometry and a table. The table all of you are familiar with, that's just a normal database, but the geometry column either will be like a lat and long column, or it will be a geometry with a CRS. Then when you're using a shapefile, I think I've mentioned this already, don't send just an SHP file. Keep in mind that the shapefile is all 4. All of them have their own strengths and weakness, but in general, use point vectors to store participles or single point like location information, store boundaries as polygons, which are two-dimensional vectors, and store remote sensing or like gradient data like over space as rasters. That way, if you have this kind of architecture set up for any of your projects, there won't be too much confusion, and a lot of other people can also use and utilize these things because these are kind of the standard way of presenting all of this. Okay, are there any questions? Okay, no questions. So this now I promised I'll talk about coordinate reference systems. So the Earth is not two-dimensional, yet we are representing almost everything about it in 2 dimensions. In order to get it to be two-dimensional, we need to apply some warping to it. So if you look at like this orange image, for example, the Earth is an orange, but when you make a map, you have to stretch it out. You have to first remove the peel, and when you try and make it flat like that, you will notice that the peel will break at certain locations. Or, the things would, if you had a stretchy peel, for example, the image would stretch. That's why in some maps you'll see North America is very long because it's towards the end of the thing and the thing has been stretched very much to a high extent. So, in order to do that, we have these things called coordinate reference systems. So, there are multiple ways to create like these kinds of two-dimensional images. And we have a lot of different ways of doing it, but we have 2 broad categories. One are geographical coordinate systems and projected coordinate systems. So most people know what lat and long is, right? Or I should say long and lat. Why should I say long and lat? It's because long is x. When you think of latitude, it is y, going north and south. And if you look at x, it is longitude. So generally speaking, when you're this is a lot of confusion happens when you're trying to do this, is that people will put x and y, a computer will expect x and y. It doesn't expect y and x. But they will put lat long into that, and it will flip everything, and it will all end up in the Arctic Circle. So just keep that in mind, that we're trying our best. We know people won't change that easily, but we're trying our best to get people to use long lat and get into the habit of saying long lat so that they don't make the mistake when they're inputting. It's a relatively easy thing to correct, but you can do it. So geographical coordinate systems basically say, okay, forget stretching the Earth out into multiple pieces. Let's just do it by polar coordinates. You know what polar coordinates are? Yes, okay. So this is why they give lat and long in degrees. They start from a center point, which is the center of the Earth, this many degrees out for longitude, this many degrees out by latitude. But you need a place to stop. Otherwise it's going into space, right? Forever. It's a single line that's going out from one particular area. So that curvature of the Earth, or the model of the Earth that we build for that, is called a datum. So if you can see that, so it looks like this. The problems arise is that the Earth is not a perfect sphere. In fact, if you look at it from space, if you took away the atmosphere is actually smoothing it out quite a bit. We have polar coordinate system. Polar in what sense? Like
fix one origin, we'll have an angle with that angle and the amplitude, that radius from the origin to that. So one is the angle and the second is that r radius, r theta we say in that. So it also gives the position.
Okay, I'll answer your question with another question. How do you know what R is?
That we have to, calculate it or measure it.
Yeah, so that is the datum. Datum is basically giving you, it is a polar coordinate system, what you're doing. Lat and long is polar. There are 2 degrees from this side and degrees from that side. So that you have 2 separate points that will mark on a map. You also need 2 points on a flat map to be able to see it, right? If you give only one thing, you can do it. I'm not saying you can't do it, but how would you tell exactly without having some kind of prior information as to where they're referring to or where they're they have taken their reference? Because you can't start from anywhere on the earth to call that. So that's why they have 2. And then the datum is your R. So you're right, this is a polar coordinate system. It's the same thing. It's just that for the convenience of mappers and for people who are using maps, we need 2 so that they can use an X and Y on a flat piece of paper. And the datum will then give you elevation based on that. Anyway. So there are multiple different ones. So for example, as I was saying, the Earth is not perfectly round. So we have this one thing called a geocentric datum, which is usually called WGS 84, which is the current standard that we're using, which assumes that the Earth is broadly fitting that kind of geodesic form. It's not a perfect circle, it will flatten out a little bit in that area. And roughly for most of the Earth, that's fine. Now you may have some countries who are saying, I don't care about the rest of the Earth. I want perfect, as perfect as possible for my own country, and everywhere else we're not mapping anyway, so it doesn't matter. Then you have like specific datums for that also. So this is WGS 84, and here we have NAD 83. So NAD stands for North American datum. So you can guess who are using that. It's usually the US, Canada, Mexico, those people, they will use that. So they've aligned their datum very close to one side of the world, making sure that their side of the world is very well mapped, but there is huge errors that happen on the other side. But they're not mapping for that side, so it doesn't matter. Here in India, we don't use a specific datum, we use our datum only, like the world datum only, the WGS 84. So there's not that much difference there. Okay, for the time being, forget all that. Just remember this, if you must remember anything. EPSG 4326, that is the code that you use to get generic lat long. Whenever a machine asks you for what is the coordinate system and you're using lat long, just type this in, 4326. Now you can use C3722, you can use 1246, things, any number of EPSG systems are there. But GPS satellites and more importantly your phone, almost everything is using 4326 in order to calculate your position. So whenever someone says long lat, they're referring to this. So just remember, even within this system, there are multiple ways to represent your position on the Earth. You can think about whichever one you may want to use for your study. I would recommend don't think about anything except this. This is usually the best one for geographic coordinate systems. Okay, projected coordinate systems. This is very much raster specific. So this is the part where you take your orange peel and you now need to stretch it or cut it up into such a way that it fits into this particular flat map that you have for the world. So there are different ways to do it. So there are, if anyone remembers the geometry, tangents and secants. So tangents means they exactly tangent on the equator. Secant means it is tangent on some other position that it is taking. Conics are perfectly fitting within a cone. And azimuth are basically like a flat surface on top of a sphere, and then the sphere is brought up towards it. So for Antarctic or Arctic measurements, usually they would use something like that. So they required reprojecting the surface of the Earth into a two-dimensional plane. Anytime you see a flat image of the Earth, this is the processing that has been applied to it. There are even more ways to project this. You may have heard of something called the Mercator projection. That is, whenever you open Google Maps and you see a map of the world, the very stretched open of the north and this thing, and you'll see India and Africa as like quite smaller in comparison. That is actually called a Mercator projection. There they have kept the equator as the correct size, but the poles have been stretched out. So rather than thinking too much about, suppose you wanted to do only a one particular region and you only want to project that into your best possible map, there is this thing called universe transfer Mercator. This is again a Mercator. You can see that the north and south are larger than the rest of the world, the rest of the equator. But what they have done is, instead of thinking too much about how you want to project it yourself, you just pick one letter and a number, follow the square that you get for that, and you can pull that out from a database and it will give you exactly what projection you need to use for that 1 degree by 1 degree. Or rather, I think this is 10 degree by 10 degree. So generally speaking, we use these as well as a way to project your maps. India, I think the Survey Commission of India uses Lambert conic, which is one of these guys. So it's basically puts India down like as a very long thing, and then as towards the edges it becomes compressed. So India is very well represented, but the borders are not. So that's what your Survey System of India uses for that. Okay, so this is a lot of information. Don't need to keep much of it in your head, but you should realize that you can just access all of this in a database that is available at this address. Oh, sorry, not this address. Actually, this I should show as well. But this is, if you just go to epsg.io, you can click on a position on the map. It will tell you all of the multiple ways you can represent that thing. You can pick the one that is best suited for you, and it will give you a machine codable number, which you can just enter into the machine, and the machine automatically knows which one you're talking about based on this. I'll just see if this is opening. Yeah. Can you see? So this is a friend of mine had made this, where you can see all of the various things, projections. So there is Mercator. You have changed the position of everything. You have orthographic, which then splits it up into this. But of course you can see, like, depending on where you are on Earth, that will be different. Now, what if I wanted to, my project was in Africa, what would I do here? If the journal has said you must use this projection system because that's our standard for the journal, but you need to use Africa, what would I do? Yeah, you just have to do this. And then now you've created a new projection system. So that's what I'm saying. There's infinite number of ways you can represent the Earth. And you might go crazy, and there are entire positions of GIS where they're only studying like what is the best way to represent your position on the Earth. So you can keep changing your thing. I can change for different things as well. So let's look at, oops, this isn't look good. Just use this, it's fine. I think this one, yeah. So of course GIS is not restricted to the Earth. Every planet also has its own geographic coordinate system. So you can do for the Earth, Jupiter, and because it's all maths, that is about geometries and spheres and like how we intersect them, anything that's spherical, you can then produce. When you're moving it, it is altering your reference coordinate. So for example, okay, let's go back to India. I don't know much about Jupiter, so I won't be able to say anything. But if I go back to India, for example, see, now India is well represented in that thing. So if I were to make a map in this particular kind of thing, or instead of orthographic, maybe we will do Mercator, which is the standard. It can alter and warp based on where your reference system is. So if I put India in the center, India as well, each of these things are there. So if I move 10 kilometers or 10 centimeters on the map, it will perfectly align with 10 kilometers in real life. But if I move 10 kilometers, say here, it's not the same because the axis of the Earth has changed completely because my reference is different. So if I wanted to get a better thing for here, I would move that into the center. But then everything else gets distorted. So it depends. If you're doing on a very local area, you want high resolution at that particular area that you're looking for. You don't want to you don't care about Africa at that point. But if you're doing the world, then you want to choose a slightly better system, right? Again, 101 ways to represent the Earth. But generally speaking, use Mercator and use this thing, EPSG 4326 for lat long. That will serve you best for most situations. Yeah. Again, that's just for your information as to like how vast the space of projections are. Don't worry about this until you need to actually do any GIS. Always set your projections prior to starting your work. So before you start any work in GIS, you say we're going to do this in 4326. If you're going to use any projected data, it's going to be projected in this particular projection. All data sets need to be standardized to that. Otherwise, what happens when one data set is in one projection and the other is in the other projection? Does anyone know? What will happen? If I were to calculate the distance between the two, one x is saying 6,000, the other x is saying 16,000. It will assume both x's are in the same place. But if that x was actually taken x from another reference, another coordinate system, it will then calculate some astronomically large number between like two places that should be very close together. So you should keep all of your projections. So before you do any analysis, your projections should be identical so that they are representing exactly the same spaces that they are supposed to be. One should not be here, one should not be on the moon, one should not be somewhere else. They should all be on the same thing. Generally, wherever possible, use 4326. Distance areas are not easily convertible into meters. So for example, if you use degrees in EP, which is the standard for lat long, is 1 degree by 1 degree in the equator the same as 1 degree by 1 degree in the Arctic? They're not. The Arctic is squashing towards the center, right? So 1 degree here is actually a very small amount of distance, but 1 degree in India is huge. So if you said, I have made this map and each square in the map is 1 degree by 1 degree for all of India. Tamil Nadu, you took that and you said it is by this much area, this much rainfall per area. But if you took the same in Delhi, is the area the same? It's not. That's why you don't want to use polar systems for things that require raster. Because then the raster itself is being squashed and stretched, and the base unit of the pixel is not representing an area in real life. It is representing a polar area, which is curved. Is this all getting through or is this too much? Okay, fine. If you're doing any analysis, remember that they can be done if all the data is being analyzed in the same projection. Okay, that's fine. So let's start with some basic concepts. We'll do visualization, distance calculation, and joining and extraction. I think 80% of your GIS work is mostly going to include this only. It's not going to be very much more than this. Yeah, so let's look at distance calculation, which is, everyone needs to know this for some level of environmental epidemiology. So say, for example, you have an air pollution monitor that's sitting in the center of your area, and you've got residents at various different distances away from that air pollution monitor. Would you assign them all the same amount of pollution? You would assume that people who are closer to the air pollution monitor are closer to that level of pollution, right, as compared to the others. So how would you calculate this? You need to find out the position of the air pollution monitor and the position of the participant, and then the shortest distance between the two. If any of you remember this geometry, all of that is Pythagoras theorem, which you will be able to calculate the distances between the two of those. But within R, you can use the SF package, and it has ST distance to calculate on the fly in meters what the distance is. There are multiple packages. There is Geosphere, and there's a couple of other packages. If you are good at maths, you can put your own equation in directly and calculate the distance as you like. Next most important thing to do, joining. So, how many of you know what a join is? In regular, okay. Madam, can you tell us?
It is the intersection between the 2 points.
That is intersection. What is joining? That is, I don't know. Okay, fine, no problem. So, whoever attended, I think, the R thing yesterday, in the package Tidyverse, there is a thing called left join and right join. If you know what that does, what it does is, you give it a reference column in your data, and say anything that matches these particular columns, you just attach it to that. So, if you're doing this without any spatial information, so for example, you have the deaths by state for one particular data set, and then you have another data set that has the state names and populations and the state boundaries. You can just join the names. You don't need to do any spatial analysis for that. So if it says Orissa and it's here and it says Orissa there, you can just combine the data together and make the same table with spatial information. And in dplyr, these are the various different types of joins you can do. So each circle here represents the one data set and the other data set. Inner join means it only joins what is not common to both data sets. Full join means everything, regardless of whether it is common or not common. Left join, which is the most common, means everything in the left data set is preserved and only the things that need to be attached will be attached to the left data set. Only the missing stuff will be attached. Right join is the same except the right data set is preferred. Anti-join means it will actually exclude information on both y and x and x and y. So judging the fact that this is being done with tables, what spatial data type do you think this is used for? Is it vectors or rasters? Which data type is tables? Vectors. This is only applicable to vectors. It's a good shortcut for many spatial things. You don't need to do any spatial analysis or anything. But rasters don't come in tables, they come in images. So you can attach information like this. So we have a map of all the districts in India. Then we have all the calculated population, like the mortalities that happened in each district. We just take the mortality data which is provided by the government. It has no spatial information. We have a spatial table, which is a vector, and we just join them, one to one. And then you can create all of these images. So that's a way of spatial projection, right? You don't need to do any fancy things to do that. What if you don't have that information? So it's not as easy to say, oh, this person is in Orissa, and this person is, this person is in some district, but we don't know where that district is, but we know where it is in space. Then you need to do spatial joining, which is an extension of joining, but instead of checking to see whether the columns are matching, it's checking to see whether the spatial extents are matching. Now, there are multiple ways in which spatial extents can match. They can intersect, meaning if they touch, if one geometry is touching the other geometry, then we join the data from there. Then if it's within a particular distance, then join. If only that is found within that. So for our Orissa district thing, if we know that it must be in some district somewhere, but we want to take the information from that, then just say intersect or like completely within. Identical is self-explanatory. If the two spatial informations match, I don't know what use case this is for, and most people won't use this. I don't think so. Because if they're identical, you would just do a normal join. Why would you do a spatial join? And then closest, or what we call nearest neighbor. So you have two competing polygons from which to draw information from, which is the closest, and take that one. That's it. So yeah, this is all fine. Corresponding raster function is called extract. Oh yeah, okay. So you can do the same thing with raster information, as I'll get to. But what happens is, vector data and raster data don't communicate with each other directly because they're completely different systems altogether. So usually what you have to do is to convert one into the other. It's a much less time-consuming process to convert a raster back into a vector. It's a much more time-consuming process to convert a vector into a raster. So generally speaking, if you have points which are vector information, and then you have raster information, and you want to get information out of that raster, you will convert the raster into points at the center of the pixel, and then assume that within that grid it is fine. So if you had a single point here, and then you can do a join, a spatial join. So if I had points and I wanted to find them on top of a raster, if suppose the point is here, then I would do this, right? Nearest neighbor. And then it will just find out which pixel is closest to that point and then join. And then you get an information for that. And if you had polygons, for example, then you look at how many points the polygon is overlapping, and then you have to apply some kind of function to it, right? Because otherwise what will happen is, this one polygon will return like 12 points. Do you want 12 points for your final data? Probably not. Most commonly, what would you do in this case? I have 12 points, I need to reduce it to 1 for only one polygon. What would I do? Say anything. Okay, is everyone stuck on this? Okay. Zoom out. But it's a vector, it's scale independent. Zooming will not change anything. No, but like I'm saying, okay. Can I get a... I want to find out the information about all of the stuff that's there. I have done an extraction, and my extraction is returned 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 points. So if I wanted to calculate some information about this polygon, and I've got one polygon and 16 points, what's the best way to then reduce this information into something that is meaningful? Take the mean. That's it. So if this was a district, for example, and these were all my temperature points, I would take mean of that, and then I'd return a mean spatial temperature for that district. Understood? Is mean the only way to do this? What are the other functions in R that will return a single value? Median. You might want median temperature. You might want maximum temperature. You might want minimum temperature. You might want the standard deviation of all the temperatures within that. So even the variability in temperature is important, because that will tell you like this district is experiencing very high highs and very low lows, and that could be like an exposure or related to an exposure that you're interested in. So particularly like vector-borne diseases and things like that. So even that is useful information. So you can use any one of those methods to do it. Of course, you can always just get 1 to 12 or 1 to 16 in this case. So that means for this one polygon information, it will multiply your table 16 times to add every single point that was there on that, which some people may want, but in most cases we don't want that. You want to take mean, median or something to reduce the information. Okay, there is one more thing that's happening here. Is this point part of it? It's not, right? But our polygon is intersecting with it. Is this useful to have this information or not? If you did a regular join, it will only take the points where the pixels are, the center of the pixels are. But the center of the pixels may or may not get included. So in that case, what you want to do is do an exact extraction. So you can do that in multiple ways in R. We'll show that in the afternoon. But an exact extraction is, it will not use points. It will convert each of these things, each of the raster pixels into polygon vector data. And then it will take the intersection out of each one, compare with the completed this thing, and take a percentage value of that. So if this was 14, if you're taking the mean of this, it will weight this differently. It will weight everything else as 1 if it is completely covered, but it will weight this as 0.33, 1/3 covered only. So that a lot of the time it doesn't matter with continuous data like temperature, because temperature is not going to vary that much across this. When will it really matter? Anyone have any idea when it will really matter to get an exact extraction? Rainfall. Rainfall is not measured as a continuous thing, because there's no negative rainfall, first of all. Secondly, you can't, so for example, if there's another district right here that's taking up this space, now this is common to both. Should both be counted for both districts? Not really, right? Either if you did it in this situation, this district then doesn't have this rainfall information as part of it. It will go into this district. or it will take this district and double count the district otherwise, if both of the districts intersect that same particular point. So then what will happen is you'll see like torrential level rainfall in some of your districts because it's being double counted by different points. So that in that case, you want to get an exact level and calculate only how much ever that pixel was within that point. You don't want to get it within, you don't want to get the whole value. You want the fractional value of whatever was covered by your point. So that's basically the exact extraction. Is it clear? Is it okay? Oh, don't worry, I'll show you an example of this. Exact extraction I don't think I have done in the worksheet as of yet, but I'll show you what extraction would look like in that sense. Okay. So just to give you an example of what all GIS software is there. Most people must be knowing these two, right? So that's your desktop-based GIS, this thing. So most of your analysis for vector and raster data will occur on this. If you're looking for specifically remote sensing tools, these two are your best options. Most of the stuff that you get from this is analysis tools. You won't actually get very much data. Google Earth Engine has almost every single data set that is publicly available for various different things. So it will have temperature, it will have rainfall, it has forest cover, it has like endless. It's like zettabytes of information on the Earth for multiple years, going back as far back as the 1950s. NV, which is, I've come to realize it's no longer called NV anymore. It used to be owned by Harris Geospatial, it is now owned by Esri. Is a particular remote sensing tool that is only does raster information the best. So if you want to create new information out of two existing rasters, which we'll get into in the remote sensing part, your best tool for that is NV. Currently, it's a one-time purchase tool. So basically, you purchase it once and you have that license for life. That may not last for very long, so please, if you can, get your hands on this as and when you can. Of course, all of this can be done by R and Python. So R and Python actually are pretty powerful in that respect, in that they can do most of these jobs pretty decently. Okay, this is just one thing I put at the end to tell everyone, please keep your coordinate systems consistent. If you are sending me a shapefile, please, I would expect to see a zip file with 4 files in it. I don't want to see like just a shapefile in that thing. Please use lat long, please don't use addresses. Addresses are very bad geospatial indicators. You know why? Street names change, positions change. Sometimes a location no longer exists within a certain place. For example, in the pin codes in the Northeast have changed completely since over the last 10 years. So if you put a pin code information now and you try to look up that information in the future, unless you have that specific information about what it was at that point, you'll never know where that person was located, and you may have to throw out that data. Lat and long, as far as I know, is not going to change. That's going to be there as long as possible. So if you're coding patient information, generally speaking, lat and long is the best thing to use. The only problem with lat and long is it's very precise. Most of the time, ethical bodies don't want you to record those things because that will give you very precise spatial information on a person, and that usually is considered identifying, and they don't want you to get identified. So ethical considerations aside, yes, don't do that unless, particularly for this thing. But in general, you can take the lat long information, as long as it's securely located, you can then jitter it. Jittering basically means you add a random value to your lat and long, move it here and there, so that you can de-identify the data to some extent. And yeah, whenever you're on the survey, you can use your device. I have my phone, and there is this app. called GPS status on Android. So what the nice thing about this is, it tells you what satellites are in the air that are tracking you at any particular point in time, how many of them are used to make a exact pinpoint location of you. Also, the elevation, you are at the height of this thing, and all of this can be recorded to within like a 5 to 2 meter error range, which is pretty good. So if your survey teams are going out, you can tell them to use this, or there are like a lot of survey tools that are built in. So whenever you start the form, it will automatically record the lat and long of the place you are currently in. That also can be done. Then have a consistent style sheet for how you want to present your data. Don't merge table rows and columns unless you're publishing, and that too on a separate file. If you merge your raw data, what happens is, if some error happens, you've corrupted your raw data. Always have copies. And then, yeah. So should we take a break? What's the time? Still have half an hour. Shall I quickly run through remote sensing? So for the most part, I don't think this is too much relevant to what you're going to do. But for your information, if any of you need to use data that needs to be derived from satellite information, or you need to create your own information, this is the topic for you. So Siddharth, I think, broadly covered most of this in his topic. So it's basically, remote sensing is what you think it is. You are sensing things remotely. You've got a satellite in space, and then you are looking down at the Earth, and you are trying to use whatever sensors are on that satellite to make, to collect information on the Earth. You can do that with satellites. Planes also do that, so aerial photography. And the thing that I use for very local or hyper-local areas, they use drones, LiDAR drones. So they will fly them over your city, and they will get like, centimeter level heights and spatial information for buildings and things like that. You can make very highly accurate models, 3D models of a very defined space, depending on whether that is useful for your data. Yes, and of course, remote sensing is an exclusively raster field. There's almost very little vector data to be found here. So remote sensing operates on how the electromagnetic waves interact with matter. So this is the electromagnetic spectrum. You have all the way from, cosmic rays down to extremely, like, I think there's radar and things like that on the other end. And we are only seeing a very small amount of that information as this. And even then, we don't actually see all of this. We're only seeing 3. We're seeing one particular wavelength of blue, one particular wavelength of green, and one particular wavelength of red in our eyes. The brain is then processing and correcting all of that to give every single shade in between. So, using this information that you have these, the sun is basically emitting all of this at once. It's emitting some more than others, but mostly it's emitting all of these rays, and they're hitting the Earth. The Earth then absorbs some of that light, and whatever is not absorbed is reflected back, usually speaking. That reflectance will then tell you something about what kind of material is there on the ground. So for example, this is black. Why is it black? Because it's absorbing red, green and blue. It could be reflecting something in some other area that we can't see, but everything that we can see is showing black. So similarly, on a sensor and a satellite, something that is reflecting black is reflecting 0 in your this thing. And as you can see, the sensors are arranged in such a way that they form raster grids. The sensor itself is like a block on a camera, and each point of the pixel is actually one individual sensor from space looking down. So it collects that information as like whatever reflectance it's getting back from the Earth, and immediately it is compressed into a raster because it's already being stored in that format, and then that is sent back down. So usually, it is a number between 0 and 255. If any computer science people here who know what the importance of 255 is. 16-bit. So if you make it 32-bit, it will be even higher. If you make it the 64-bit, it will be even higher. But 16-bit, generally speaking, is a good midway area. You will get enough detail because most of your computer graphics and all of that is operating on 16-bit colors, usually speaking. Some of them operate on higher ones. You get very good resolution on that. Plus, the information that you get isn't difficult to transmit. It's low enough resolution that it doesn't require like a huge amount of energy to, or very clear uplinks to send the information back down to earth. So yeah, maybe I'll show this later. I'll show this first. So this is us. This is what we are seeing. We see these three. We see only in red, blue and green, and then we make up all of our information on the world on that. The world is of course a much more colorful place than just this. It can be all of these. So generally speaking, the modern old satellites used to do this plus one more, which is infrared. Modern satellites now use multiple bands, this many, so much. So each band is recording a very specific wavelength that is being reflected, and those are useful for some level of like analysis that people want to do. So currently we are at this generation of stuff. There is now enough computational power and like technology is advanced to such a level that we no longer do this. We are just absorbing all whatever information comes in directly. Any wavelength, it will be split by itself by the computer, and it will be stored rather than as discrete blocks like this. It's one single thing, so you get like the full spectra. That so far they've not only started launching those satellites. At least for the next few decades, I would think it would still be this. You'll get information like this, where it is broken up into these narrower bands, which are more than RGB, but are just, you can get more information out of it. So knowing that, you can show this. These are all the different bands that are available for Landsat specifically. Landsat is a particular satellite that people use for land use analysis. So Landsat 1 and 5, like I said, 4 bands. You have green, you have red, and you have 2 in your infrared. So they didn't bother about blue initially. Because as far as they were concerned, they were doing mostly analysis for vegetation. Vegetation doesn't require blue. Then Landsats 4 to 5, they started adding more information onto the satellites. And as you can see here, this is the pixel resolution of each. Why is the pixel resolution higher here than it is here? Why are we able to capture at a higher resolution for low frequencies than we are for high frequencies? The answer is here. Yes, correct. The wavelength is large enough for these ones that it might actually miss the sensor. So what they do is they have to increase the resolution of the sensor, the spatial resolution of the sensor, so that such that they are not missing anything from like a smaller thing. If they narrowed it down even further, this will mostly show black. So they have to increase it out a little bit so that they know that they're not missing information. If it is actually black, then it is actually black. That is mostly the reason why for long wavelengths you want to keep it that way. So here are some combinations for Landsat. This is the one you are most familiar with, red, green and blue. That will give you, sorry, not this. This is different. This is completely different. But you usually want red, green and blue to use what you call natural color images from space. So your Google satellite images are generally in red, green and blue because that's what you would understand as this thing. Now this is false color images where you take band 7, band 6 and band 4 and combine. This will give you where it's urban based on this. So for example, if you had a city that was painted green and you viewed it from space, you wouldn't actually be able to tell whether it was a city or not, right? because this, at least from your perspective and from that distance, you are seeing everything is green. So you'll assume it's a green place only. But the thing about concrete is it can't hide this. It will reflect a lot of shortwave infrared radiation back out, which a plant will not do. So for camouflaged things like that, you can actually spot a city quite well from satellite information if you can do these false color ones. Ditto for this color infrared, which is 543, that shows vegetation as a deep red, which you'll see here, and it will show urban as blue. This is the most common one here. Then there's for agriculture, land, water. All of these, you have to take all of the band information and then substitute it into red, green, and blue so that you can see it as different ways of looking at the world. So yeah, these are your 4 resolutions for satellite data that you need to think about when you're going to download this information. Spatial resolution, which is how big is the pixel. So if I want to, if all of my data set is within a 1 kilometer area, if the whole pixel is 1 kilometer, everything is going to be assigned the same value. I can't use 1 kilometer then for that. I want to see some variation in that 1 kilometer radius that I'm collecting. So I would need to look at Landsat, which is 30 meters. But the problem with Landsat is temporal resolution. Landsat crosses the same place on Earth every 16 days. Is it okay for my study that I'm doing that I get my information once every 16 days? It may be true. You could, at least for whatever you want to do, you could probably get your every 16 days may be perfectly fine. But if you're looking at daily exposures of say temperature, then you can't use this because you're only going to get your information every 16 days. Spectral resolution. Does this satellite have the bands I'm looking for? So if I get my information from Landsat 1 to 5, there's no thermal band on that. But my study is on temperature. So I can't use Landsat 1 to 5 for that because they're not calculating any temperature information from the information that can be got from there. And then, will they be enough for what I need it for? Then there's radiometric resolution. This, don't have to worry about too much. Most of the time, other people have decided the radiometric resolution of those satellites. But in general, does the band accurately capture the frequency of light exposure that I am this thing? So basically, is it able to distinguish how green this plant is? So if the green band is like sort of somewhat going into red or blue, then it may get information that makes it look like a place is green, but it's actually greenish blue, not quite like this thing. So you want narrow bands to see only that one particular data set that you want to show. Anyway, these are some satellites that you might want to look into. So Sentinel-2, which is best for green space and urban areas. So neighborhood level analysis, you can see your spatial resolution is between 10 and 60 meters. Pretty decent for spatial resolution, but your temporal resolution is every 6 days. And yeah, this is another thing to be wary of. We have data in 2012. You can't use this. The satellite was not up at 2012. So I think if your study is more and more recent, you will find yourself having more and more satellite information to choose from. But if your study is quite older, then things get a little harder to decide how you want to do, and you might have to make some sacrifices in terms of spatial temporal resolution. Then Landsat 8 and 6, so for historical land use, you can get up to 30 meters with thermal at 100 meters every 16 days from 2013 to present. But historical Landsat can go back as far back as 1972. So this is very good for long-term changes in land use. So if you want to take a photo of Vellore and track its development for the last 40 years, that's what you want. This is what we are mostly using in our analysis, which is MODIS at 1 kilometer every day from 2000 to now. They have 2 satellites, Terra and Aqua, where they go over at different times. They're called sun-synchronous satellites, meaning that they exactly at the same time each day they are at the same place. They move with the sun. Then you have Sentinel, which is mostly for trace gas air pollution, so NO2 generally speaking. And but again, for only 2017 to now, but very good resolution. And if any NO2 models usually use Sentinel-5P. VIIRS for light time nights and like fire activity. So if you're tracking like stubble burning in Punjab, you may want to look into these. And then there's the GPM NASA for precipitation and disease. You can use rainfall estimates to predict mosquito breeding sites like dengue. But of course, not very good in terms of spatial resolution. But that might not matter to you. So depending on what you need to use for your study, you can pick the satellite of your choice and process the information. Yeah. So generally, we don't want to use raw band information because that will just tell you what the sensor is seeing. What the sensor is seeing is not exactly something that you can translate into useful information. So you need to process this information down into something that is usable by you. So I'll take an example here, which is NDVI. Most people know what NDVI is, right? It's basically a proxy that you use for greenness. Greenness in this sense meaning plants. Not greenness in the sense of greenness, but like, yeah, plants that you want to use. Now, here's the theory as to how we come across, how we utilize NDVI. Plants have this thing of hating infrared, like to an amazing degree. The greenness of plants is actually from this tiny bump. They actually absorb green light quite well, but they only, they eject it more than blue and red, which is why they appear green. But if you were to be able to see infrared, plants would blind you with how much infrared radiation they're reflecting back. If you take an infrared camera and look at plants in the daytime, you'll just see a white image. They're basically reflecting everything at 100%. Healthy vegetation does that. Unhealthy vegetation doesn't do that as well. And soil doesn't do that at all. So now that you know from this band information, I can tell which would be vegetation because it's reflecting a lot of this and not. I can then use that information to construct an index, which is this normalized differentiated wetlands. So it is the amount of near infrared light subtracted by the red band divided by the sum of both. So from this you would get a value ranging from -1 to 1 theoretically, because if one is 0 and the other is full, or if both are equally transmitted, you will get different values for both. Likewise, we have found other things that are useful ways to look at that. So there is NDBI. Do you know what NDBI is? So this is normalized differentiated vegetation index. What is the normalized differentiated B? Built up area. Buildings do the same thing that plants do with near infrared. Shortwave infrared radiation, they reflect a lot. If you noticed, if you walk around at night for a building that's been exposed to the sun, the building is slowly radiating something like heat outwards towards you. That's this that you're sensing. And water does the same thing, but in reverse. Water absorbs a lot of shortwave infrared radiation, but does not absorb a lot of NIR. And then you can have a normalized differentiated water index, which will tell you to a very high degree whether some place is underwater or not. So this index now gives you a range from -1 to 1. So -1 to 0 generally means there's no plants there. Urban usually tends to be 0 because it reflects infrared and red to a similar degree back out to space, depending on the color of the place. But it's usually 0 or in rare cases -2. If you see -0.5 downwards, you're usually looking at water. Then from between 0 and 0.33, the plants are not doing very well in that particular area. Or there are plants in that area that are not like trees. They are grasses or shrubs or things that are in like hardier plants that are not having that much chlorophyll to reflect back the infrared. Then from 0.3 to 0.66, generally speaking, you can say they are healthy plants, and 0.66 to 1 is full greenery in that particular area. If you have one, you're in a forest. Now, there are studies also that have gone and have got each individual species of plant, figured out what range of NDVI they would give off in like a healthy or an unhealthy state, and they have published that information. And if you want to get down into that level of detail also to try and figure out how many plants are there of that particular type, there is a way to do that, but that's quite advanced. You can do that later. And plus, you wouldn't want to use just NDVI, because NDVI will also reflect for other plants as well. There may be other plants that reflect in the same thing. You'd want something very specific to that plant. There was a colleague of mine, Adam Glick, he's the one who did a study of counting every single tree on Earth. And he has discovered that there is more trees on Earth than there are, like, what was the thing? Just 3 trillion trees. We had more trees than we thought we did, basically. So he used a combination of NDVI calculation plus shape detection to try and figure out how many trees there were in there. So this is something that we did for Bangalore for another workshop. We had downloaded the information from Landsat. Then we did this, we took both the layers of near infrared and red, so calculated NDVI, and then we've got this map of Bangalore showing where the trees are, where the water is, where the buildings are, and where there is dense vegetation. There are 1 or 2 pockets of Bangalore that have dense vegetation, but as you noticed, Bangalore in general is not very densely vegetated. Okay. How much time do you have left? And then we're good. Okay. So I'll just quickly touch on reanalysis data. I think Siddharth also mentioned this in his presentation. So when we want to get information from satellites, again, we have a lot of problems which we may not get, accurate information for particular times and dates and things like that. And this is an ongoing problem for, the entire world. So a lot of people, what they do is they build huge data sets of everything that we know about the world. We put it together, we model it out, and then we create these huge data sets called reanalysis data sets, which are using actual data, but to predict also over the entire world for days that we don't even have data for. So up to 1950s to now, and they're still creating this information. So they include temperature, rainfall, wind speed, boundary layer height, atmospheric pressure, and then they give a great picture of the atmospheric going on. So here we have millions of daily readings from weather station ocean buoy satellites. They have this model called NWP, which they make the forecast, and we nudge this model to match reality. So why should we use this for exposure assessment? So for example, if you don't have like a temperature monitor for that particular area, or you don't have climatic data for that particular area, 24/7, 365 days a year you have information available. Any variables like wind speed and direction, which generally most people don't use, you will also get from these kinds of reanalysis data sets. Things like planetary boundary layer. Does anyone know what this is? Planetary boundary layer. It's otherwise called mixing height. So if mixing height is basically at what height of the atmosphere is the particles moving around or interacting with each other. So if you noticed in winter, pollution tends to stick to the ground, and in summer it goes back up again. So that what is happening is actually the cold weather is reducing the mixing height, and the pollution is not able to escape a particular height of that level. So in the models you generally keep planetary boundary layer or boundary layer height as one of the variables, so that you understand that the pollution is not moving that much. And in the daytime or in the summer, the boundary layer height increases, mixing increases more, pollution is encouraged to move up, and then it can get dispersed also from that way. So one of the ways to actually get rid of your pollution problem is to increase the temperature in that area. But it's not a very practical solution. Then so a trend line for climate change is real. So why should we not use it? 31 kilometers is the reanalysis data resolution for ECMWF, which is one of the reanalysis providers that we use. They freely provide it. It's very good for climate. It's not very good for exposure, because exposure, generally speaking, you're wanting to find as much variation as you can within that particular small area that you're studying, or in general. So recent updates, of course, have made it up to 9 kilometer, but is that acceptable also for your analysis data? For certain people, that may be enough, because that you need, what's more important to you is the temporal, non-breakage of that. You want constant data. But in some cases, that might not be acceptable as well. Few pixels can cover the entirety of district. It cannot distinguish between a park and a busy road. Of course, this is simulated data. The one obvious criticism that any reviewer of your paper will give is, this isn't reality. We don't know what you have done. You downloaded something and done something. So yes, that is a criticism of that. Rainfall and cloud cover are notoriously difficult to get perfect with reanalysis, which is fair enough. Rainfall, of course, you can't, within the 31 kilometer range, you're going to not get very precise rainfall for a particular area. It will, some of that area will include the sea as well, sometimes on coastal areas. And then most reanalysis models do not fully understand things like urban heat islands, which are very local effects. So they're very local to the buildings that are there in that particular area, unless coupled with urban canopy models. So this is what we are doing with some of the work we're conducting at CCDC and Ashoka. So this is 1 degree by 1 degree in Krishnagiri Tirupattur area. IMD provides free of cost 1 degree by 1 degree temperature information for this entire region. So this entire region will return, I think in IMD it's something like 28 degrees. Now if your study area, all of the participants are in this one particular area, they've all got the same exposure. So now let's look at reanalysis data, which is slightly better, 16 times increase. So now you can see that there's some variation. Some areas are hotter than others in comparison, but still quite coarse for what we want to get for exposure modeling. Now we do something called as resampling, where we create 1 kilometer by 1 kilometer raster grid cells, and then we approximate or take average distances. We do something called spatial interpolation to try and guess from the ECMWF data what the pattern would be at 1 kilometer by 1 kilometer. So it's not actually understanding anything about the world it is doing there, it is just averaging it out as best as it can. So that's what it looks like. Then this is a model. So we have now taken all of this information that we have, including data from stations and things like that, combine that information, we have made an understanding of how the world is then affecting temperature. So for example, here we have added how many roads and buildings are there in a particular area in that thing. And then we compared that with the model for temperature, and we found that buildings are, as we expect, increasing the temperature in that particular area. So therefore, if you're near a building, you're increasing your temperature. So we believe that this is a more accurate representation of what the actual temperature density is in there. But depending on which set of data you use, you will get very different results in your final study. So we built a model like this for temperature, and we've also got one for PM 2.5 from 2008 to 2020. That's what we've been using for our analysis to try and see. Thank you. Any questions? You can ask any question from any point in the slide. I'll go back and look at it. Shweta?
Is it really true that your colleague counted every living tree?
I'm sorry?
Is it really true that every living tree was counted?
Yes. I can share that paper with you if you want.
That's quite.
It was quite an intensive process, as I recall. It took like 5-6 years of constant computer analysis to try and figure it out. But it was, again, he counted every particular tree in the latest year in which he had done it, which was 2018. So that was 4 trillion trees in 2018. Now we have to redo the analysis again, and then you'll keep running into that. But yeah. Any other questions? Okay, good. I'm expecting everyone to do very well in the workshop part then.
If I want to differentiate between heat exposure pattern between urban and rural areas, so which indices would be better for me to see?
Indices is in satellite indices.
The indices which was which was told, the vegetation index, water body index, and then.
Oh, okay. So you're asking a different question. You're asking what indices affect temperature.
I want to differentiate between heat stress among the urban and rural areas. I want to know. So which indices I want to go about
Okay.
checking?
You're asking, there are two different questions here. Are you assessing how much heat stress is expressed in a particular area?
Difference in heat stress between the urban and the rural areas.
That's not a remote sensing problem per se. That is a exposure analysis problem. So that you will go into environmental health, occupational health, those areas. They have various things called heat indices, which you use to calculate this thing. So in general, we use shade temperature, which is ambient temperature, whatever is reported in the newspaper by IMD, we use that. There are also these things called heat indices which take into account humidity, they take into account solar radiation, the clothing you're wearing, apparent temperature, all of that goes into this thing. The gold standard for now, for as far as heat stress is concerned, stress being the effect of heat on a person, that is stress. You're deforming your body's thermostasis is the word. The deformation of thermostasis is the thermal stress. That can be calculated by an index called UTCI. Then there is another index that is used by the military and by occupational health professionals, which is called WBGT, which takes into account 3 indices.
Wet
Wet globe temperature. You know this. Okay. So those are that. Now for the modeling part, which is another thing, which you're taking satellite information to model those things, what you would do is you have your information for a particular station, and then you have all of the satellite information that is pertinent to that, and then you are predicting heat or one particular variable or ambient temperature over a particular region. So for that, you need things that you know that heat is related to. For example, we know that presence of water bodies nearby decreases heat levels or ambient temperature levels.
Yes.
So that would be one thing you input into your model. Vegetation decreases temperature. That is another thing in your model. Urban heat islands, concrete roads, all increase temperature. That has to be a factor in the model. So if you're modeling for these heat stress variables over a particular area, you would need to collect all of that information. You have to do some literature review to find out what all are related to your things, or you can also check and see from your own experience or what you think might be.
Because as you said, urban heat islands was one of our factor. So which data set, which satellite image would be better, if we want to take?
I would go for Landsat for anything related to land use. So yeah, 30 meters, which is decent for urban areas. You are not going to do much more analysis than that in those areas. Otherwise, the other thing you can do is take Sentinel-2 if your analysis has to be done for various, recent years, from 2015 onwards. That will be from 10 to 60 meters. You can get the various indices.
The resolution is much more closer.
What you're describing is land use stuff. So land use stuff, you use the land use satellites, basically. You want high resolution, but you don't care about temporal space that much.
Thank you.